Hello, everyone. As we discussed, we are going to cover a simple validation case. It's a rectangular channel with these dimensions, and we are going to apply different wall heat fluxes and step between these values to investigate different parameters that we are looking for. So these simple problems are very helpful if we want to set up a validation case for our boiling model before we move to more complex problems. This is an overview of our duct model that has a body of fluid. We have a heating element here. It's a solid that is embedded inside the fluid. So we are going to apply the heat at the bottom face of this solid and investigate the boiling at the top. So a couple of things that is important here. The name selections is very important. So we have identified our inlet, outlet, liquid wall, and solid wall. So these are uh, basically where we want to define the boundary conditions influence. So we need to have name selection there. The other important thing is shear topology. So if we review the shear topology, we have already defined shear topology between the uh, uh, solid heating element and the fluid. So this is carried over to the fluent, so we don't have to worry about it. So next step is to move the CAD model to fluent meshing. So we use the watertight geometry workflow here. So by clicking this, it takes us to ANSYS Fluent meshing interface. We are in the ANSYS Fluent meshing interface. The geometry has been imported. So you can see there is solid body and fluid. We move to the local sizing. We don't want to add local sizing here because there is not very complex geometry here, but it definitely has capability to add local sizing based on the body of influence, or you can define an object and define local sizing. Definitely, if we have mesh quality issues, we use this option. Uh, Generate the surface mesh. Here we are defining minimum and maximum size for mesh. So uh, this heating element has a 2 millimeter height. So I would add 1 millimeter or minimum size, and the maximum element size I'm going to reduce it to 1 centimeter. The growth ratio is basically how this minimum is going to grow to the maximum size, and like lower growth rate results in a smoother transition, but 1.2 um, is a good number to have there. So generate the surface mesh. Yeah, we can see the surface mesh quality is good. Uh, we have both fluid and solid defined in our model, in our CAD model, so we don't want to cap the regions because we already have the fluid there. Change all fluid boundaries type from wall to internal. We only have one fluid, so there is no need to change this. We already defined the shear topology. There is no multi-zone meshing here. We just described the geometry. The name selections that we had is already transferred into the fluent meshing interface. So inlet is velocity inlet, outlet is pressure outlet. This is the most reliable boundary condition for getting faster convergence. Solid wall and wall liquid, they're all defined as walls, and we want them to be walls because we want to model the heat transfer between the walls. Okay, so we update the boundaries. There is only one fluid in our simulation, so we create the fluid region. Uh, Here we are going to define solid and fluid region type. So Fluent does a good job in finding the names and matching the names uh, with uh, uh, with the region type. So if I click on the liquid, you will see it is assigned a fluid type. So update regions here. Here is add boundary layers. So um, I'm going to add three boundary layers for both fluid and solid region. It's usually a good practice to add boundary layers to solid as well if we running a conjugated transfer problem. So this is a fluid region here, three boundary layers. I'm not going to change the growth rate. Uh, so add boundary layer for the fluid. It shows up here, and then we go to the solid region and add three boundary layers as well. So we're all done. We can generate the mesh. The maximum mesh size I want to use is 1 centimeter, and let's go ahead and generate the volume mesh. So as we can see, three boundary layers are added to the solid and into the fluid, and this is the look of our mesh, which seems accurate enough for our simple problem that we want to investigate. The other important thing that we need to check here is cell count. So like this is about 13,000 cells, which is quite low. And the minimum quality, orthogonal quality, is zero point 0.2. So anything above zero point 0.1 considers a good is being considered a good quality. So we're good in terms of mesh quality and in terms of cell count. So we're going to go ahead and move to the Fluent solver. In the Fluent, to save time, I've already set up the model so we can review together. So in the Fluent, usually the workflow is we are going from left to right through these windows and through this workflow. So domain mesh, if we don't see the mesh, we should click on the display and it displays everything. So we have inlet, outlet, walls, everything is being shown. You can take a look at the units or close or change them. The quality is always good practice to check the mesh quality. So check perform mesh check. So if there is no error messages, we have it done in the console. It means there is no error messages. We are good to go. Okay, so the next step is physics. In the general tab, because it is a we have uh, natural convection together with the force convection. We need to activate the gravity. So I'm using for gravity, I'm using the named expression. G is the gravitational force. We are putting it into minus C. So if we look at the model, the heating element is here, so minus C is correct. We are running a steady state case, and it's a pressure-based analysis. Operating conditions, again, the input temperature for is 288.16. Bassinsk model, it always require operating temperature. It is needed for natural convection, flow, and it helps us to get faster convergence compared to problems with density as a function of temperature. So we use the Basenic's operating temperature variable density parameter. So there is a user input here. So this is needed for boiling models because the density is variable. So operating density is a name selection that we are going to define pretty soon. So this is an existing name selection, operating density, and we are going to define that. Operating pressure is again another name selection. Is expression. It's an expression. It's not name selection. It's an expression that we're going to define. So it's a function. We're going to define all of these in the user defined tabs. So this is the view of the operating condition. And if we move to the next tab, because we are running a heat transfer problem, we need to turn on the energy to solve the energy balance. Uh, the viscose turns blue. It means that it is automatically turned on. So the flow is going to be turbulent. We need a viscose model. So we are using K omega steady state, which is a well-established and versatile model for turbulence influence. So we're going to use all the default values here. Next, we are going to move on to the multi-phase. So the model is mixture. Please turn off the slip velocity. Um, turn off the implicit body force, and the interface modeling is dispersed. So we need to move to the phases and define our two phase. So we have two phases here. We have water and vapor. So phase material, we have already defined water liquid, water vapor in our material that we are going to review next. So how to define our materials for liquid and vapor. We're going to review that next. So we assign water liquid to the water. For the vapor, we assign water vapor. Phase interaction. Here we have different surface tension parameters, but for boiling simulation, we need to define real gas properties table. That is, again, we are going to review it next, how to bring in this table. This is a table generated by Fluent and defines the phase change in the water going from liquid to vapor. So we have already imported this table. It's already here, so we're gonna select that one, and uh, we can pick any of these, vapor or liquid, doesn't matter. Um, we need to define the heat mass and reaction. There is a mass transfer from water to vapor, and mechanisms is evaporation and condensation. So there are different mechanisms here. There's cavitation, user defined. So there is an option for evaporation and condensation. This is our model that we are using to define the evaporation behavior. So uh, as we discussed, we are using semi-mechanistic boiling model for two-phase. So this is the Lee model for semi-mechanistic boiling. Uh, these frequencies from phase and two phase shows how frequently uh, a vapor bubble is turns into the water or vice versa. So uh, 25 and point 1 is a good starting point, but this is something that needs to be fine-tuned by experimental data and experimental observation. Saturation temperature, again, we are using the RGB table. So this is the table that we are going to load into the fluent, and I'm going to show you how to do that. Boiling parameter, bulk temperature, length scale, uh, boiling model advanced setting. We're using Chen. Like we don't change uh, most of the parameters on the right hand side is in the advanced tab. So we are not going to change most of these parameters. So one thing to note is this Frosted-Zubler transfer coefficient. This is where the latent heat transfer and nucleation boiling is significantly increasing the uh, heat convection coefficient. So this is the formula that Fluent is using for capturing that effect. Hit OK and move on to interfacial areas. There's a water vapor interface area. So we are using symmetric condition for that area. And that's pretty much all the setting that you need for multi-phase. So apply and close. The next tab in the physics is the material. So here we have fluid and solid material. So for fluid, I've already uploaded the water liquid and water vapor. So it's quite simple. You can go into the Fluent database and copy this material to your model. And for solid, I have aluminum defined here. So before going to the cell zones and boundary conditions, I think it makes sense to go to the user define and show you two things: how we read the table, like real gas properties table that we use uh, in our physics tabs when we defining the multi-phase behavior, and also we use a lot of expressions when we were setting up this or operating conditions, right? So for operating conditions, we had operating density, operating pressure, and we are going to use more uh, expressions when we are defining the boundary. So let's go ahead and look at first how to read in the RGB table. So this is the option here, read table. So I have already read the table in, so it's a RGB table set. If you don't have this table, there is a Python script in Fluent that can generate this, or you can use the CFX. There is a built-in app in the CFX that can generate this RGB table. Basically, it defines water, vapor, and liquid phase different properties, pressure range, temperature range, and it basically defines the phase diagram for the water. So once you have read in this table, it is available to be used in different places in the Fluent. The next thing that I want to show you is the name expression. So is If we go to the manager, these are all the different expressions that I have defined. So we have in the temperature. So basically, if we open it, it is the name is in the temperature. We set it up to 368.15 Kelvin. So in name expression, we always need to define the units. It shows where it has been used. So inlet, all the inlet conditions are using this parameter. Inlet velocity, the same. So if we look at it, the inlet velocity is almost zero point 0.4 meter per second. We have operating pressure. We have operating density. Let's look at the operating density. It's set to 0 kilogram per meter cubic. Operating pressure is defined here. Outlet pressure is defined by a formula. So this is the formula. So it's a function of the density. So the density of the mixture minus the operating density times gravity. And this is basically taking into account the buoyancy effects. So the outlet pressure is identified through density. We have outlet temperature is set it's basically the same as output and inlet, and this is where we define uh, the flux, the heat flux going to the heating element, right? So, and we are gonna change this value when you have an expression defined here. Changing is very easy. You just need to come in here and like you can manage all your boundary conditions basically here in this window, right? And also you can use it for parametric studies later. So now we understand how to import the phase diagram, how to define this name expression. Let's move back to the physics. Let's go to the cell zones. For the fluid, if we double click on it, opens up the edit window. So the zone name is fluid, phase is mixture. Don't have to change anything else. Only thing is in the multi-phase, it is a boiling zone. So for your fluid, you need to activate the boiling zone. For solid, it's a mixture, and the other important thing is always check your material here. So the material is assigned aluminum to the solid, and also if we go back to the fluid, it should be because it's a mixture. It is gonna pick it up from the fluid region. Next is boundaries. So if we look at the inlet, so in the inlet, again, phases mixture, velocity magnitude. We have a name expression with the name inlet velocity. The gauge pressure is 0. On the thermal side, we are defining the temperature. We again have a name expression here. For outlet, if we look at it, it is a pressure outlet. We are defining the outlet pressure as a name selection. And again, for the outlet, we have the outlet temperature defined here. All other uh, conditions are wall interior or wall condition. The only other thing that we need to check is this solid wall where we apply the heat flux to the bottom of this heating element. So it's a solid wall as the name. We are applying heat flux to it, and the heat flux is wall heat flux is a name expression. So that's the only parameter we want to change here, and close. In any moment, if you wanted to check any of these boundary condition visually, you can go in here into the display. For example, I want to see where is this solid wall, so I'm gonna remove everything. I put the solid wall here and display, so it shows me the solid wall here. Now let's move on to the solution tab. One thing that we want to check is the solution method. We want to set the solution method to coupled, and we want to set all the parameters here to second order upwind. So density, momentum, not the volume fraction, turbulence, specific dissipation, energy, and pseudo time method is global time step. Then let's move on to the residuals. These are the residuals that we are going to monitor. Under the show advanced options, we want to set the convergence criteria to none, and we want to iterations to store is 1000 iteration. Okay, then we're going to initialize the before initializing is a good idea always to save the model. So I'm going to save it first. Yeah, so we are going to initialize the model and calculate it. I've already finished the simulation here to save time. So a couple of things you can define definitions, surface reports to monitor the parameters that you want to see the convergence. That's one of the things that you can use as your monitors. So we have residuals here. We are monitoring, but you can always add additional reports. Yeah, as I mentioned, I've already run this problem, so it is we just show some quick overview of the results. So this is a movie playing back the vapor volume fraction. So if we play this movie, you will see that the heating element, like this is the vapor volume fraction, we completely turn everything into vapor, and once we turn off the heat, it cools down. So this is a quick demo of how we can set the boiling problems in Fluent. We are going to look at a more complex problem, which is a two-phase flow in a microchannel setup in our next video. Thank you.